Okay, so this question is about question number 5 and 4 from the lab. What is for number
Wait,
4?
five and
Oh, 3
six.
and 5 and 6.
5 and 6, yeah.
Okay, so processed food has the mass in metric and English units. So let me get you some processed food here. So what I'm going to do is I'm going to switch my share screen to a new share. And what you're going to see here is some Boboli pizza sauce. And here we have 15 ounces and 454 grams. The 454 grams are metric units and the 15 ounces are English units. So that's an example of some sort of processed food that has both masses on the box. Now I'm going to go back to my share here with the question here. So here we have metric and English units. They're equivalent. So find two solids that have a metric and English measurement of mass. They should have different masses. So that means that you would find something else other than Boboli pizza sauce. Maybe a candy bar. Candy bars have these on them. Or if you eat something more healthy like a granola bar. Take photos of both, clearly show the masses, and use these equivalencies to convert the mass of the store ruler to ounces. So now I'm going to change my share here to the Elmo. So from the Boboli box, I have 425 grams is equal to 15 ounces. Now, I don't know what your store-bought ruler weighs, so I'm just going to invent an amount and say that my store-bought ruler weighs 6.76 grams. So the directions ask you to convert this from metric to ounces. So I want to go from 6.76 grams to ounces. And I will be able to do this directly if I have an equivalency that has grams and ounces in it, which I do above. So what I'm going to do is I'm going to take my 6.76 grams and I'm going to multiply by this equivalency. One of these goes in the top and one goes in the bottom. The one that goes in the bottom is going to be 425 grams because I want these to cancel. And then I'm going to put 15 ounces in the top. And that's an abbreviation for ounce. Now, based solely on what we've learned about significant figures, this has 4. I don't know where the extra 7 came from. Who snuck that in there? Which one of you? I'll find you out. Okay, 6.76 grams, which is 3 Zig Figs. 15 is 2 Zig Figs. And the 425 is 3 Zig Figs. Now, in reality, whenever you have something on a box or some sort of conversion given, the reality is that you have 3 Zig Figs here, and this is really supposed to be exact, which means infinite Zig Figs. Okay, so whichever of the two numbers has more significant figures, the other one is exact. Okay, so here is the calculation we need to do, and we can kind of estimate the answer, if you will, because here, this is roughly 7. 7 times 15 is roughly 100. 100 divided by 425 is roughly a quarter, so the answer should be around 0.25, but less than that because I kind of rounded things up. So I plug these numbers into my calculator, and we have 6.76 times 15 divided by 425, and we get 0.239 ounces. And so my ish of about 0.25 was not too bad. I have 3 significant figures because with these food conversions, the one that has more significant figures is how we limit the significant figures in our answer, plus the other numbers considered to be exact. So, Harry, how does this look for you? Does this kind of explain what to do for that problem?
Yeah, no, that explains it a lot,
Okay,
actually.
now, of course, your second way of doing this, you're going to find a different conversion. So for mass conversions, you're looking for solid processed food, although I would argue that pizza sauce is not solid processed food. But when you see grams there, that's what you're looking for mass. Now, for a liquid, you want to look for like a soda can or something like that, where they're going to have something else. Here's another example of something where you could use the numbers from this disinfectant spray. We have 12 ounces and we have 340 grams. Now, in this case, the 340, it doesn't really have a decimal there, so we assume that's 2 zig figs, and the 12 would then be 2 zig figs or infinity. It doesn't matter. Okay, so you're supposed to find out that we are surrounded by conversion factors. Okay, so I'm going to go back to, well, I'm going to leave it right here and ask, does anyone else have a question? Please raise your hand, or no, actually don't raise your hand. Turn your mic on and please ask. No questions? I'm not looking at the chat, so that's not going to work. Okay, then you asked for it. Here we go. I'm still going to use this time to show you how to do problems and what kind of things I'm expecting on an exam.
Wait,
So
Mr.
this is in the, oh, does someone have a question?
Yeah, I have one more question, just a clarifying one.
Yes.
On the homework, on question 9, when it says convert data to 1 over the amount and 1 over the velocity, are you just putting 1 over like 1.96, plugging it into the calculator and then writing down that number?
Absolutely.
Okay.
So if we take a look at that homework, and actually, you know what, I'm going to put that question on hold for just a moment. Is this on? Who was asking that question?
Oh, I did. Harry
Who was
did.
that?
Harry.
Oh, Harry. Okay, we need to go back to number 6 because we didn't do that one. I just want to touch upon that. So do we understand for number 6, you're going to use the value from the graduated cylinder and you're going to use metric conversions that you get from liquids. Okay? So now fast forward to the homework problem that someone just asked about. Let me change my share to my browser. And what I'm going to do here is I'm going to go to the module and I'm going to go to the homework in module 1 or module 2. So here's the homework. Oh, that says module 1 homework. I should edit that because it should be module 2 homework. Okay, save this sucker. I see this is due Tuesday. And someone just, I'm not sure who asked about this, but this is a great question about number 9. And you can see that we have these amounts and we have this convert data to 1 over the amount and to 1 over the velocity and make a table of these results. So here, I'm going to change my share in just a minute. And I'm going to share my Elmo. Okay, so this is what we're asked to do. Make a table of 1 over the amount and 1 over the velocity. So For the very first entry here, I'm going to put 1 over 1.96, but I don't want to leave it that way. I want to actually put this into my calculator. Actually, I guess I can do 0.19 or clear 1.96 in this, and I get 0.510. So I want to do that with each of the values for the amount. And as an example for the reaction velocity, we would do 1 over 4.75 times 10 to the minus 5. You'll notice I put parentheses around 4.75 times 10 to the minus 5. And we know that this answer is going to be actually quite big because 10 to the minus 5 in the denominator becomes 10 to the positive 5 in the numerator. And 1 divided by 5 makes it about half. No, wait, 5 goes into, yeah, 0.5. No, 1/5, 0.2. So this will end up probably being around 2 times 10 to the 4th. So let's check that out. 4.75 second EE negative 5. And we get, I don't like that. I'm going to put that in scientific notation. And I get 2.10. Actually, that's wrong. 2.11 times 10 to the 4. And here the 0 becomes a 1 because of that 5. So we want to do that for each of the entries in amount and reaction velocity. So the answer to the question is, do I just divide each one of those into 1? And the answer is absolutely.
Okay.
Now, if we talk about drawing the, plot this data and plot 1 over the amount on the x-axis, it's going to look like that, and 1 over velocity on this axis. And here, I can tell by looking at these numbers here that this 0.51 is probably going to be, I guess, a little bit on the smaller side. If we look at the 0.16 and see what that comes out to be, that's going to be 6.25. So when I'm graphing this, and I'm going to put 1 over the amount here, I want this end of my graph to be about 6, because that's going to be my largest value. I don't want to put 6 here because it means half of my graph is not going to be used. Now for my velocities, which one is going to be the largest velocity? And it might be that 0.585 one. So the 0.585 is this 0.585 times 10 to the minus 5. Now I'm going to show you a little trick here. The number I get is 1.701 times 10 to the 5, but I'm not going to write it that way. I'm going to write it as 17.01 times 10 to the 4. Now, why am I doing that? And the answer is, if I have both of these raised to the same 10 power, it makes it a lot easier for me to see which one is smaller and which one is larger. If we look at 1.701 times 10 to the 5th, and we compare that to 2.11 times 10 to the 4th, most people, including me, have a hard idea of figuring out which one's bigger and how much bigger. Now, if I look at 17.01 times 10 to the 4 versus 2.1 times 10 to the 4, I can see that this number is about 8 times larger than this one, because I'm comparing oranges and oranges, if you will. Okay, so that's a little trick. So this is going to be my biggest number. So my velocity, I'm actually going to put times 10 to the 4 here, and I'll make this value 20, this value 10, here's 5, here's 15, and then here's the 17.01 value. It's going to be somewhere around there. And so this will be one of my points, 17.01 times 10 to the 4 and 6. And notice that the table is made so this looks kind of like X and this looks kind of like Y. And X is the X-axis And of course, y is the y-axis, or the vertical, and x is the horizontal. So that's more than you asked for. This is just to give you an idea of how to graph it also. You want to make your graph big. If this were, I'm assuming, of course, that this was a full piece of paper. Honestly, for graphs, if you draw them out on a piece of paper, so you should get yourself some graph paper, that's the minimum, half a page. That's the minimum size graph you want. It's better if you use the whole page. Okay, so good question. Other questions, please.
You said you weren't looking at the chat, right?
No, I don't look at the chat because I only have a 13-inch laptop.
Right.
And I just can't see all that stuff on my desktop or on my laptop.
Oh, somebody asked, this is Jackie asked a question in the chat. It says she's not able to speak, but she has a question about problem 8 with determining the number of sig figs.
Okay. Number 8 on this one?
Yeah, on the homework.
Okay, pure ask.
Looks like.
Okay.
Yeah, on problem number 8 of the homework. So.
Okay, so for this, each one of those numbers has 3 significant figures. A lot of people think that just because you have a whole number that it's exact, and that's not the case. Okay, so each of those has 3 significant figures. Now, if we wanted to figure out how many significant figures you get from averaging something, let's take a look at that. So we're going to look at the first student and their values. And the homework problem asks, sorry, folks, I'm trying to minimize the little distractions that I have here. So for you, not your partner, but actually we'll do your partner, not you. So your partner gets values of 138, 137, 138, and 138. When we add these all together, we're going to get roughly what? 560? Or more than that, 580? Let's find out. 138 times 3 plus 137. So we get 551 degrees Celsius. To get the average, we take the 551 and divide by 4. And my calculator writes out 137.75. So here we have to understand that when we're adding these together, each one of these is good to the ones place. So since they all end in the ones place, this is also good to the ones place, which means right there at the end of that number 1. Now, when I divide by 4, the fact of averaging is that we have exactly 4 trials or 4 different temperatures, exactly 4. So this has infinity zig figs. Now this, it's good to the ones, but since we're now using it in a division, we have to know that this has 3 zig figs. So when we finish doing the averaging, if we have 3 zig figs and an infinity zig figs, we want to cut this down to 3 zig figs, so it becomes 138 degrees Celsius. So that would be the average. Now, the percent error, technically, we're not supposed to round until we actually finish everything. So for the percent error, the proper way would be to take this 137.75 degrees Celsius, but still remembering that we're supposed to have rounded there, minus the accepted value, 135 degrees Celsius, divided by 135 degrees Celsius times 100%. So that's how you calculate the percent error for the partner. You do the same thing for you, but with your values, okay? So here, if we do the subtraction here, we get 2.75 degrees Celsius. But here, since we're doing subtraction, this is good to the ones, this is good to the ones, so this is only good to the ones. And I'm keeping track of that. Divided by 135 degrees Celsius times 100%. And now we do our little magic. We can kind of see that 275 times 100 is around 275. 275 divided by 135 puts it around 2%. Okay, so what do I round to? Well, I know that this only has 1 zig fig, even though I've carried some extra along. This has 3 zig figs. So here, 1 zig fig. This is 3 zig figs. And this is infinity zig figs because that's the definition of how you get percent error. So we round to 2% error. Okay. So this is the what the book means by carrying extra digits along, but not rounding until the end. So we have to keep track of where things would be based on the previous operation and then how that would carry forward. Okay, so since Jackie doesn't have her mic, maybe she's chatting to y'all and saying, okay, I got it. All right. Now, if we take a look at which set of data is more accurate, here, smaller percent error, more accurate. And looking at the data from the first person, I think that's going to be closer to 135 and have a smaller percent error. Now, what about precision? Well, there's many different ways to look at precision. Precision. I told you the down and dirty way, just to look at it and decide whether it's very quickly, is smaller range, is more precise. So here, who has the smaller range? The student, you, or your partner? Well, you have a range of 3 to 8, so 5 degrees Celsius, really 133 to 138, which is 5 degrees Celsius. Your partner has a range of 1 degree Celsius. Your partner is more precise. Their values are closer to one another. You know, if I had to guess, I would think that your partner is just lazy and wrote 3 numbers down at the same time, and then another number that was close. Okay. All right. So that's one way to deal with the precision. And I think that's a lot easier than doing the standard deviation. The standard deviation is something that you can set up on your calculator. Here's the standard deviation button on this calculator. So I probably have to make a list of some sort. And I'm looking for an obvious little thing that has a list. Here, memory variable. That may be my list, or maybe data. Data, stat, error. What I'm doing here is I'm just playing with it to see how I might use this data button. How about stat button? Oh, one variable stat. Okay. I don't know how to use that button. So I'm going to clear that. This is what I would go for which is more precise. Okay. We don't do a whole lot of standard deviation calculations in this class, I'll be honest with you. But you tend to do them a lot more in a physics class. So be ready for that. Okay, so Jackie, chat away, and did we take care of your question? I'm going to assume we did. Let's see, more. Can I look at the chat? Oh, there's the chat. Yes, thank you. Okay, excellent, Jackie. Okay, who's next? We're on a roll here. Don't be afraid to ask questions about anything. Because if you don't ask questions, I'm going to ask questions. Now remember, I'm not looking at my participant list, so you've got to vocalize your question. Okay, that being said, you asked for it. So what I'm doing here is I'm looking at study questions from the back of your book. Okay, so this goes along with the very first chapter of the, I think it's the first chapter of the 10th edition. Oh no, that's the review. I'm in the wrong section. So let's take a look here. So here are things that you should be able to do. I'm going to put the problem up here. I'm not going to copy it. In the following scenario, identify which statement represents a theory, law, or hypothesis. And that's it. So how about A? A student exploring the properties of gases proposes that if she decreases the volume of a sample of gas, then the pressure exerted by the sample will increase. What do we think? Is that a theory, a law, or a hypothesis?
A hypothesis?
I agree. And why do you think it's a hypothesis?
Because she's going to be testing things off of, she's exploring the properties. So explore hypothesis.
Exactly. You test hypotheses. And when you don't really test a theory, you test a hypothesis and then you add that to a theory. Okay. How about B? Many scientists over time have conducted similar experiments and have concluded that pressure and volume are inversely proportional. Is that a theory or a law? What do you think? Well, it turns out that it's a law. Okay. A lot of times you might find the difference between a law and a theory is that a law is something where you don't have an explanation. No explanation whatsoever. You just notice that this is always the case. Pressure and volume are inversely proportional. You increase the pressure, volume goes down. That's what inversely proportional means. One goes up, one goes down. Okay. So usually and very often laws don't have explanations. They're just, we notice this fact. So B, I'm going to have to call a law. How about C? Proposes the reason this occurs is that if the volume is decreased, more molecules will collide with the given area of the container walls, causing the pressure to be greater. Now, that would be something that I would consider to be a hypothesis, actually, because that's something that you might be able to test. How would you test something like that? And the answer is you could use less gas because it should have fewer molecules, or you could use more gas because that should have more molecules. For C, I think some people might think that that might be a theory. And, you know, I'm not sure that it is because you could do a lot of experiments to show that this type of thing is going on in A. And then this could be the idea behind it. So, you know, it really depends on what part of the experiment or research you're doing for C. All right. We're going to skip 3. We're going to skip 5. And we're going to go to number 7. So this is something that you should be able to do at this point in time in your chemistry career. Don't worry, we're going to get to harder ones soon. You don't need to name these out loud, but I want you to name them mentally, and then I'll say them. And If you're correct, you give yourself a little slap on the back. Okay. A, carbon. B, potassium. The reason it has the letter K is it's for the Latin name of callum. C, good, chlorine. You see how I did that? I assumed you got it right and I said good. D, phosphorus. A lot of people confuse potassium and phosphorus. Potassium is the K. E, magnesium. And F is nickel. Now, all of these you should be able to name also for 8. But we're going to go on. Let's take a look at 9. What is the symbol for barium? Correct, it's Ba. How about B, titanium? Correct, it's Ti. So a lot of times you'll find that the symbol is the first 2 letters. Not always, but often. How about C, chromium? Cr. How about lead? Lead is actually Pb, and it's based on the Latin name. Arsenic, As, and zinc, Zn. Okay, so enough of those. Let's take a look at this next one here. Number 11. In each of the following pairs, decide which is an element and which is a compound. So how about A? And the answer is Na is an element, NaCl is a compound. The reason we know Na is an element is because that has the single symbol of one element. The reason we know this is a compound is because it has 2 symbols of elements and there's no space between the symbols. How about sugar or carbon? Well, we know carbon is an element. It's on the periodic table. Therefore, sugar must be a compound. Gold or gold chloride? Well, these are names. And the fact that this name only has one element in there, and this name has 2 elements in there, gold chloride, I've got to assume that gold is an element and gold chloride is a compound. Okay. Now, let's take a look at this one, because this one actually takes a calculation. And I'm going to write this one out so that we have it for posterity's sake. And let's see, I need to unzoom. Where's my little remote?
Can I ask a quick question about the discussion?
Sure.
So if we ask questions in the new Zoom setting, do we still have to post questions in the discussion?
Yep, absolutely.
Okay, thank you.
And the real reason for that is that I don't keep track of who's asking what questions where in a Zoom session. And when you post online, I have a record of that. So I'm going to flip this piece of paper over so I can use the other side. And let's take a look at this problem. An 18-gram sample of water is decomposed into 2 grams of hydrogen. So I'm going to put H2 instead of the word hydrogen. And 16 grams of oxygen. What masses of hydrogen and oxygen would be prepared from 27 grams of water. Okay. And what law of chemistry is used in solving this problem? So the law will be the law of definite proportions or constant composition. Now, let me show you how to approach a problem like this. So we have 18 grams of water can be turned into 2 grams of hydrogen and 16 grams of oxygen. So this is, if you will, sort of a chemical reaction. And this shows the law of the, actually, I should say, there's also the law of conservation of matter. So we're actually using both of these laws. Here, we start off with 18 grams, we end up with 18 grams. That's the law of the conservation of matter. We're going to use the law of the definite proportions to actually solve the rest of this, and that would be this way. We can actually say that 18 grams of water is equal to 2 grams of hydrogen is equal to 16 grams of oxygen. And the word I should be saying here is not equal, but equivalent to. So this means that if you start with 18 grams of water, when you're done, you will get the equivalent of 2 grams of hydrogen and 16 grams of oxygen. So I put all of these as equal, okay? Because they're equivalent, if you will. So imagine if I start off with 27 grams of water and I want to figure out my grams of hydrogen. Well, I would want to start off with 27 grams of water, and I would want to multiply by something that has grams of hydrogen in the numerator and grams of water in the denominator. Now, why is that? Because I want the grams of water to cancel. So we can cancel the unit and the label together. Now, where am I going to find this equivalence? And the answer is, it's right there. So I would put 2 grams of hydrogen here, 18 grams of water, and this is really the law of constant composition or definite proportions that we're using here, where we're saying that, you know what, the percentage of hydrogen should be the same for 27 grams of water as it is for 18 grams of water. And here's that percentage for all practical purposes. Okay, so when we multiply this out, 27 times 2 is 54, and 54 divided by 18 should be roughly 3. So we should get roughly 3 grams of water. Let's turn this on and see what we get. And we do get 3 grams of H2. So how would we figure out grams of oxygen starting with 27 grams of water? So 27 grams of water. What do you multiply by to get grams of oxygen? Go ahead and take a moment and set this up and give it a shot. I'm not going to ask you to show me your work or anything like that, but write it out. It sticks a lot better than if you just think about it. While you guys are thinking about it, I'm going to have a little bit of my coffee. Okay, so if we take a look here, we want to use the 18 grams of water and the 16 grams of oxygen. Which of these two am I going to put in the numerator and which in the denominator? Well, I'm going to put the 18 grams of water in the denominator so that the unit and the label cancel. And I'm going to put the 16 grams of oxygen in the numerator, the north. And so here we're going to have 27 times essentially 1. So this should be really close to 27 grams, but not quite. And we can actually kind of figure out the answer, because here, if 3 of the 27 grams become H2, the balance, or 24 grams, should be the amount of O2. So let's do the calculator work. And we get 24. Okay, are there any questions on number 13? This is the kind of work, this, and this, that's the kind of work I would expect to see on the exam for your answer. If on the exam you simply wrote this as your answer, if you wrote that on your exam as the answer and showed nothing else, and this were a 10-point problem, I'd probably give you 1 point. And that's it. Okay, so it's important, I'm trying to emphasize that it's important for me to see your work when you're doing calculations. Okay, this is another one that we can do without showing our work. We can think about it. So let's look at number 15. In each case, decide if the underlying property is a physical or chemical property. Now, for me, I would normally ask you, well, tell me why you think that's the case. Okay, so A, the color of elemental bromine is orange-red. You know what, I'm gonna open up the participant list. And here, let's practice using our yes or no type stuff. So here, if you think this is a chemical property, that bromine, elemental bromine is orange-red, put yes. If you think it is not a chemical property, but it is a physical property, pick no. If you're having a hard time deciding, I can help you. Because I see some of you aren't choosing. So this will help you. That didn't help? Okay. So let's take a look here. Maybe you don't know the answer, so you don't want to even guess. That's fine. So what do we use as our rubric, if you will, for determining whether something is a chemical or physical property? Well, a good way to look at it is for a physical property, is this a property that actually changes the substance somehow, or would be different for a little bit of the substance versus a lot of bit of the substance? Actually, I shouldn't say that for that. Is this a property you could determine without changing the stuff into something else? That's a good way to look at physical properties. So here, elemental bromine is orange-red. Do we need to turn bromine into something else to see that it's orange-red? The answer is no, so that's going to be a physical property. How about B? So let's go ahead and clear the field. And I'm going to clear all. And this time we're going to use thumbs up and thumbs down. Iron turns to rust in the presence of air and water. Thumbs up for chemical, thumbs down for not chemical. Okay, we're overwhelmingly agreeing that this is a chemical process, and it is. This is one of those things where when we say it turns to rust, rust has different properties than iron, so therefore I think it's a chemical change. So when you have a change in your whole set of physical properties, it's probably a chemical change. How about let's clear all. And let's go with hydrogen can explode when ignited in air. If you think it's a physical property, give me a thumbs up. If you don't think it's physical, give me a thumbs down. That's right. It is not a physical property. Explode is a reaction. Does anyone know what hydrogen makes when it explodes in air? It's water. When hydrogen reacts with oxygen, it makes water. That's why a lot of people think of hydrogen as the ultimate clean fuel. When it burns, you don't get a greenhouse gas, you get H2O. And the oceans are loaded with H2O. So this is not anything that's harmful. Okay. How about the density of titanium? Metal is 4.5 grams per centimeter cubed. Physical property or chemical? Well, you don't have to change the titanium into something else to get its density, so I think it's physical. And it is physical. All right. We're going to move on. So I'm going to zoom out here. I want to get to some more calculation type problems. All right, this is a good one that incorporates a lot of what we've just been talking about. A piece of turquoise is blue-green, solid, with a density of 2.65 grams per centimeter cubed. You'll see me do this a lot instead of this. I really don't like this, and I'll tell you why in a bit. Okay, and it has a mass of 2.5 grams. Okay? So, which of these are qualitative and which are quantitative? Qualitative. And the answer is blue-green, solid. And which ones are quantitative? 2.65 grams per centimeter cubed and 2.5 grams. So quantitative simply means it's got a quantity in it, a number. Qualitative is more descriptive. B, which is extensive and which is intensive. So remember, extensive depends on how much of it you have, and intensive does not depend on how much you have. So that means that blue-green is intensive. The density is intensive. And the mass is extensive because the more mass you have, the larger the number. Now C asks us, what is the volume? So we want to start with our 2.5 grams and turn that into volume. Can we do that directly? Well, here, they don't tell us what volume to get. So I'm going to get the volume in centimeters cubed because of this right here. So this conversion says I can go from grams to centimeters cubed. Now, if I do this, do the grams cancel? And the answer is they don't. So this won't work. So what if I put this upside down? Would that work? Oh, this isn't 2.65, it's 2.5. I'm sorry. That would work. Is it real easy to see that the grams cancel? To me, it's not. Okay, is it really easy to see that the grams cancel because one's in the numerator, one's in the denominator? Yes. This is not clear. Do not write fractions in this class with one of these little, what do you call those? Hashtag, what is it? Forward slash, backslash. Don't do those. Write them like this. This looks so much better. And here, how many significant figures are we going to have in the answer? Well, we have 2 significant figures here. Here we have 3. And the fewer numbers, where we only have 1, that's infinite. So we have 2, 3, and infinite. We get 2 sig figs. And can everyone see that the answer is going to be close to 1 because 2.5 and 2.65 are very close? So clear, 2.5 divided by 2.65, and we get let me change this to decimal. We get 0.943. And the answer is centimeters cubed, and there's our volume. Okay? So that's good. Now, I have got to run because I've got to go back to school and give out lab kits. I know that some of you have already come by and picked up your lab kit, and I met you, so that was great. Hopefully, I'll be seeing the rest of you this afternoon or Tuesday. This afternoon, I'll be there from about 1:30 until about 6, and that's why I've got to jet out of here right now. Because I'm going to be at school, I don't know whether or not I'm going to be able to how do I say this? Post this particular Q&A as soon as I'd like, but it should be up there later tonight. The next lecture that would have been today, I will post later tonight because I'll come home and do the lecture in front of the Zoom. I'll put some stuffed animals up over here in front of me so that I can talk to them and feel like I'm talking to an audience. Maybe they'll even laugh at my jokes. And I'll post that Zoom session for the lecture in the lecture videos. But this is going to go into a Q&A video or module 1. Okay, that being said, I hope you find that the new way of doing the Zooms is going to be more informative for you and that you learn more from it. And by videotaping the lectures and having you watch them, even if the lecture goes really fast, you can kind of pause it, rewind it, listen to it again, and write down any questions you may have from those lectures that you watch to ask during this time for clarification. So are there any final questions here? There being none,
Nope, thank you.
What room?
turn your mics on and say goodbye to everybody.
Bye, everyone.
Thank you.
Bye, everyone. Have a good weekend.
Bye.